Alright, so I'm going to actually give you a nice little intro to optimization. And if you're watching the video, you'll notice at the top, the homework, I've changed it only to go up to number 10. That actually only will leave you a few problems to do because I am going to do numbers 1, 2, and 3 from the textbook as examples. So let's start off with actually knowing what optimization is and the process for it. So optimization is just a fancy word. It's the fancy way of saying finding extrema. So finding a max or a min is essentially the same exact thing as optimization. We tend to use the word optimization when we talk about real life problems, problems where you're building something, things that are a little more realistic than just giving you a function. So to start off, let me go through the process. The first thing you really want to do is, if you can sketch a situation, sketch a diagram of the situation. And sometimes you just can't or you don't need to. Secondly, what function are you optimizing? And this is where you'd make that decision of, are you finding a max or a min? And then right next to it, you would write the name of the function and the equation of that function that you're going to be optimizing. So step 3, use any other given information to substitute out a variable. So this is where we were talking about, you want to optimize a function, then you want the function to be written in terms of only one variable. Once we do that, step 4, you're going to find the extrema. And I am purposely going to write this with our 5 steps. First step, your domain. Check if there's a realistic domain. Check if that domain ends up giving you endpoints. Find f prime of x. Set f prime of x equal to 0 or undefined. And what's really nice about these problems, because they're real life problems, we tend not to have to worry about the undefined. Because we're doing extrema, I still follow the same process where I don't want to forget to think about undefined when I do extrema. And then we do the f prime sign chart within domain. Using endpoint. So I've gone through, I'm actually hoping that you are writing notes. So if you have not copied down the notes, I am not giving the same notes in class. We're going to continue on doing new problems and doing example problems in class. So please make sure that you write down the process for optimization. If you look in your chapter 4 packet under section 4.4, there should be some room inside of there to write the process. So really, if you look at the process, the only thing that's new are steps 1, 2, and 3. And that is actually where students do tend to have trouble, is just writing out their own function. So let's start off with some examples. And actually, before I do that, I'm going to copy over the process so that I can refer back to it and it has the steps. And you guys can see on the screen the steps and not have to have them memorized. So there we go. All right, so let's start off. You have 40 feet of fence to enclose a rectangular garden along the side of a barn. So this classic problem, they call it classic because almost every single calculus book you ever look at this is one of the starting problems. Now, you have this barn, and you're going to enclose a garden. And here's the odd thing that they don't mention, but the garden will be along the side of the barn, and therefore you won't build the fence around or along the side of the barn. So there's actually only 3 sides of the fence. So they want to know, so there's my picture. I'm going to start off with writing out that I'm going to maximize the area of the barn. So area, we usually find length times width. Now the problem is we have 2 variables. So far I've sketched the graph, I've figured out what I'm optimizing, and now I'm going to use any other information to substitute out a variable. So right now I have 2 variables. The length and width, I'm going to go back up to my diagram. I'm going to call the length and width, I guess, x and y. So now I'm going to rewrite this as x and y. Problem is it's still 2 variables. There must be more information given. So if you look back up, we ended up with 40 feet of fence. That 40 feet of fence is going to be important. That is actually going to be what creates this red fence all around. So when you talk about going around a shape, you're really talking about perimeter. And the perimeter of that fence would have been 2 x's plus a y. The perimeter was 40. Now, you want to make sure you understand, we've already decided that area is what we're going to maximize. So I don't want to make the mistake of trying to take the derivative of the perimeter. The perimeter is 40. Now I'm going to use that to substitute in. So I'm going to solve for the easier variable to solve for, and that's going to be the y. So there's my y variable. So now I'm going to substitute that into my area. And now we have a much more simplified version. Let's see. There's my area. So things that you really want to think about. Now, you're going to actually find the extrema. We're going to physically find the maximum now. And so I got to think about a possible domain. Now, I will tell you, the only reason we do this is to decide if there's really a closed endpoint. So if we're talking about 40 feet of fence, you should realize that the domain for this guy would be 0 to 20. And the reason being, if the length of the x was 20, then this would also be 20, therefore leaving us no room for the y. There would be a fence literally stuck next to the other fence. It would look something like this. There's the fence, and there's the fence right on top of it. So it makes no sense. Now, if it was 20, if the x was 0, then you'd actually end up with 20 along the y, and the fence would have no depth. So you should realize that this function that we have here is not going to have endpoints. That's really all I want you to figure out. If you can't understand the domain, therefore you don't figure out the domain every time, really, like I said, you're looking to see if the domain causes endpoints. So in this case, we don't have endpoints. That's what we're trying to make sure we understand. So I'm going to come over here, try to keep the problem on the same page. Now that I did my endpoints, I'm going to find my derivative, which is 40 minus 4x. Set that equal to 0. We don't have to worry about undefined because it's a real life problem. If your x is undefined, if your a prime is undefined, you're really not going to find a realistic answer that works. Let's see, so 40 is equal to 4x, x is equal to 10. So what is the maximum area that you can enclose? So I've figured out that x is equal to 10. I'm going to double check right now that that is actually a maximum because I don't want to get my problem wrong. So my a prime is 40 minus 4x. That's a line that slopes downward. That's what it would look like. So my sign change is positive to negative, so this is definitely a maximum. Now that I know that that's a maximum, I can answer the question. So the max occurs when x is 10, but that wasn't the question that was asked. It asked us what's the maximum area. So the area would be 40x minus 2x squared. So that would be 400 minus 200, which would give us an area of 200 feet squared. So now I have actually a few practice problems from your textbook. We're just going to literally try each of them together. That way you will not have to do these separately. So let's start off with this guy. We have the sum of two non-negative numbers is 20. So let's start off with two non-negative numbers. There's an x number and a y number, and when we sum them, they're going to equal 20, and x and y are both greater than 0 because they're non-negative. It looks as though it can equal 0 because it just says non-negative. Find the numbers if the sum of their squares is as large as possible. So let's look at this. The sum of two non-negative numbers has to be 20. If both numbers have to be 0, we are going to end up with a closed domain. I'm probably going to stick with variable x, but my domain will be 0 to 20. The reason being, 0 is the smallest number we could have, therefore the other number would have had to be 20. The largest number we could have then is 20, where the other number would have been 0. So we do have endpoints. Let's look at part A. Says the sum of their squares is as large as possible. So let's start off with the word max because it says large. The sum of their squares. So we'll call the function s, and sum of their squares is as large as possible. I'm going to look at my equation that I have there, and I'm going to see that I have two variables. So I'm going to have to use some more information to eliminate one of the variables. So I am going to use what we have right above in purple. I'm going to solve for y and get 20 minus x, which means I'm going to substitute that back into here and square it. Now, I'm going to choose not to simplify this. I'm going to just take the derivative as is. So now that I have one variable, my next step would be to actually find the extrema, and I would do that by finding the first derivative. And the reason I can do that, I already found the endpoints earlier. The first derivative, I'm going to do a chain rule right here. Derivative of the outside, leave the inside the same, multiply by the derivative of the inside. Let's simplify that, and we get, let's see, 2x plus 40 minus 2x, and then we're going to times that by negative 1. So we end up with, this would turn into a negative, this would turn into a positive when I distribute that negative symbol, so we get 4x minus 40. Alright, so there is my first derivative. I'm going to take my first derivative, set it equal to 0. We're not going to worry about undefined. 4x equals 40, therefore x equals 10. I'm going to put my endpoints. There's my 10. We only do a sign chart over the domain that we want to use. There's my 0, and the function was 4x minus 40. That would be a line sloping upwards. The slope is 4, and the y-intercept is negative 40. So my symbols would be negative 2 plus. So what do we figure out? We figured out that this is the minimum, which is not the question that was asked in part A. If we're going down, flat, up, then this is a max, and this is a max. Therefore, we'd have to figure out which one is the max. If x equals 0, remember the sum of the two numbers ended up being 20. You do realize that the other number would then have to be 20. In this case, if one number is 20, then the other number would have to be 0. They're actually the same answer, and so I just have to go back and make sure I answer the question. It says, find the numbers if the sum of their squares is as large as possible. So There are the two numbers. They're either 0 and 20 or 20 and 0. Same exact answer. Part B says, actually, we don't need to take it over. One number plus, oh, I just realized I did not answer part A's second question, which says, find the sum to be as small as possible. And that would be x equal to 10 and y equal to 10. So this would be the minimum. Now part B, we can go on, says one number plus the square root of the other number. So we're going to add, so I'll just call this function s. One number plus the square root of the other number is as large as possible. All right, so what do we get? We had in the beginning that the two numbers had to be 20. They summed up to 20. We know that we have endpoints because the largest and smallest numbers they could be in general are 0 to 20. I know what function I'm going to maximize. Therefore, I'm going to use the other information to simplify out a variable. So I end up with the square root of 20 minus x. Now that I have only one variable, I can take my function, find its first derivative, 1 plus, and remember this, is x plus 20 minus x to the 1/2. So, bring the power down, subtract by 1, leave the inside the same, multiply by the derivative of the inside. So we end up with s prime is equal to 1 plus -1 divided by 2 root of 20 minus x. Please follow the same thing we did before. We're going to get a common denominator because you want this simplified as much as possible. So common denominator, we would multiply this by 2 root 20 minus x over 2 root 20 minus x. So we get 2 root 20 minus x minus 1 all over 2 root 20 minus x. We're going to set our derivative equal to 0 by taking the numerator and set it equal to 0. We're going to take our derivative, set it equal to undefined, and we won't have to worry about that. Let's see. So we end up with adding 1 to the other side. We get 2 root 20 minus x equals 1. Divide by 2. 20 minus x equals 1/2. Square both sides. 20 minus x equals 1/4. And it's not plus or minus because when you square a number, it's always positive. And then we end up with x is equal to 20 minus 1/4, which would be 79/4. So let's hope that that is the correct answer. We'll have 79/4 right here, 0 here, 20 here. Remember that this is, I'm going to backtrack. I'm actually going to backtrack. I'm going to say that I do want to solve for the derivative equal to undefined. And the reason is I want it on my sign chart. I don't ever want values to be missing from my sign chart. And so we end up with 20 minus x is equal to 0, so x is equal to 10. 20, 0, 10, 79/4. All right. Where this guy went. There it is. Oh. So we have that the derivative is 0 at 79/4. The derivative was undefined at 10. And so, let's see. Wow, that was actually supposed to be a 20. That makes a lot more sense. All right, So now let's do our sign chart. See where we're looking. I am going to highlight the part of the sign chart that I'm actually going to look at, which would be the numerator. The denominator is always going to be positive. So I'm going to pick the number. Wow, the sign chart is a hot mess. So let's fix this before I try to move on. The sign chart for s prime would have 0, 20, undefined derivative, and 79/4 is right here with a 0 derivative. I am so sorry. So let's put in the value of, let's say, 10. And so if I put in the value of 10, that would be a positive. See, make it look a little nicer. And then if I put in, say, 19.999 and take the derivative, sorry, and then take the derivative, substitute it into here, you'll end up with negative. So we end up with a maximum at this value. I should not have crossed this out. I am a mess today, Friday, and I'm tired. All right, so we have the maximum here. There's an undefined derivative at 20, but we're actually okay to use 20 because our domain was 0 to 20 closed. So I answered the part A, then it asked me as small as possible. So, wow. So now we're increasing, flat, decreasing. So my maximum must be at the, sorry, my minimum must be at the endpoints here and here. And if you remember, because they add up to 20, it's the same exact number. So my maximum happened at 79/4, that would be one number, and then the other number being a fourth. And then the minimum happens at 0 and the other number being 20. I will do one more, which is the maximizing the area problem. See, actually, we did a maximizing area, but let me see. I'll do this one too. All right, so we have that the largest possible area for a right triangle whose hypotenuse is 5, what are its dimensions? So let's just start off with right. We're going to draw our picture, a right triangle with a hypotenuse of 5. We are going to maximize the area of the triangle. Here's your base, here's your height, and the area of a triangle is 1/2 base times height. We know that there are two variables, b and h, so I must have more information to use to be able to eliminate a variable. Now, it's a right triangle, so the only thing I can think of that relates to all three would be Pythagorean theorem. So we get that h squared plus b squared equals 25. Pick a variable and solve for it. We get b is equal to, it's actually the plus or minus square root, but since we're dealing with real life problems, we're only going to care about the positive square root. Let's substitute that back into the formula here. Area is equal to 1/2, the base being square root of 25 minus h squared times b. All right, so now that we have that, let's talk about endpoints. Is it possible for you to give a domain with endpoints? Now, if you really think about this, let's talk about the base. You should realize that the smallest base that you could possibly have would be this tiny, infinitely skinny triangle where the value of b is getting really close to 0. But it can't actually be 0. And the fact that I know that it can't be 0 means that this has no endpoint. You don't even have to finish trying to find the maximum value because there are no endpoints. So I will say the max would actually be 5, not included. So let's take this function here. Let's rewrite it. I'm going to bring the h in front and then write this as such. Now, things that you have to understand, you cannot distribute, you cannot simplify this at all. The only thing you could do is rewrite it with a 1/2 power. And now that I have that, I can all right, so I can see, chop this over. I'm going to take this to another page so that I can work with the function. So what do we get? We get this guy here. I'm going to find its derivative. A prime is equal to product rule. I'm going to do a product between 1/2 h times that other function. So the derivative here would be 1/2 the negative 1/2, 25 minus h squared times negative 2h plus the 1/2, 25 minus h squared to the 1/2 power multiplied by the derivative of 1/2 h, which is just 1/2. Let's try to simplify this as much as possible. In this case, this h, this h, this negative 2 will stay in the numerator. The denominator will have this 2, which makes 4, and this term here, which is the square root of 25 minus h squared. In the purple term, everything is, everything here stays in the numerator, the 2 is in the denominator. So you should be able to see that we are going to multiply this side by 2 root 25 minus h squared over 2 root 25 minus h squared. We end up with, negative 2h squared plus 2 times 25 minus h squared. The square root of this times the square root of this just cancels the square root for you. Divided by the common denominator, which is 25 minus h squared. So let's simplify this as much as we can. We get in the numerator, it looks like negative 4h squared plus 50. The denominator is 4 square root of 25 minus h squared. We're going to set the derivative equal to 0, which would mean take the numerator, make it equal to 0. I'm going to put a little note here. And then over here, we'll do f prime equal to undefined, which gives us the 4 root 25 minus h squared equals 0. Let's solve each of these. We get h squared is equal to 25 over 2. H is equal to the plus or minus square root of 25 over 2. On the right side, we end up with 25 minus h squared equals 0. H is equal to plus or minus 5. So let's make our sign chart. If you remember, our domain was 0 to 5. We're not allowed to use the 0 and the 5 because they were not real endpoints. We ended up with an undefined derivative at 5. We end up having the plus or minus square root, but the negative square root wouldn't fit on our sign chart, so we end up with the square root of 25 over 2. If you wanted to rewrite that as the root of 5 over root 2, that would work too. You just have to be able to figure out a number to the left and a number to the right. So a number to the left would be 1, a number to the right would definitely be 4. So I'm going to use 1, substitute into my most simplified derivative. If you look at the denominator, if you look at the denominator, it's always going to be positive because 4 multiplied by the square root has to be a positive value. So I'm only going to use the numerator. If I substitute 1 into the numerator, this would be positive. If I substitute 4 into the numerator, it would be negative. Therefore, I end up with a maximum. If I could get this pen back. A maximum at root of 25 over 2. And let's see what the question asks us. What are its dimensions at the maximum? So the dimensions would be that 25 over 2 is one of the lengths of the sides, and then the other side, the way we would find it is if we go backwards a little bit. I found h was the root of 25 over 2. So then I would square that value, get 25 over 2. I would end up with b is equal to the square root of 25 over 2. Let's see. So the values are the actual same values, 25 over 2, and the base being 25. with a roof. All right, so you can see that you're doing the same process as before, and the only difference is that you are figuring out your domain, your endpoints, and a picture with the equation using realistic, real things. The first few problems you have are maybe not as realistic as the maximizing the volume that we did in class, and we'll kind of look at that when we get back on Monday. Thank you.